Hi, in this video we are going to talk about dynamic resizing and other features of the associative arrays. So let's get started. First of all, let me tell a few words about load factor. Basically, it is the number of entries divided by the number of slots or buckets, or basically the size of the array. So n divided by m, this is the load factor. If it is 0, then the hash table is empty. If it is 1, then the hash table is full, because it means that the n is equal to m, and basically the m is the size of the array, so how many items can we store in the array, and the n is the actual number of items we would like to store. So that's why this n divided by m is going to be the load factor. If the load factor is approximately 1, it means that it is nearly full and the performance will decrease and the operations will be slower. Why? Because if the load factor is approximately 1, it means that the hash table is nearly full. If the hash table is nearly full, then the probability of collisions are going to be very high. And if there's a high probability of collisions, then we have to solve these collisions either with open addressing or with chaining. If we use chaining, then there will be lots of items in the linked list, and the order 1 constant time complexity will be reduced to approximately linear time complexity. If we use, for example, open addressing, then we have to make several rehashing, and that's why the algorithm will be slower. So the load factor is approximately 1, then the operations will be slower. If the load factor is approximately 0, it means that the data structure, so the array, is nearly empty, so there will be lots of memory wasted. And basically this is what I've been talking about, that there's a trade-off between memory waste and operations running time. If we waste memory in the sense that the array is nearly empty, then there will be no collisions. And if there will be no collisions, of course, then the hash map or the dictionary or whatsoever is going to be very fast, because there will be no collisions. We are able to do the operations in order 1 constant time complexity. If we do not want to waste memory, okay, then there will be much more collisions, and the running time will be slower. So that's why there's a huge trade-off between memory complexity and running time complexity. So the final conclusion is that dynamic resizing is needed sometimes. Okay, so the performance depends on the load factor, as we have discussed in the previous slide. And basically what's very important is the number of entries and number of buckets ratio. The space-time trade-off is important, as I said earlier, and the solution is to resize the table when its load factor exceeds a given threshold. In Java, when the load factor is greater than 0.75, the hash map will be resized automatically. What does it mean, that 0.75? It means that whenever the 75% of the array is full, then we have to resize the underlying array data structure. In Python, the threshold is 2 divided by 3. What does it mean? That we have to resize the underlying array data structure when it's 66% full, in the sense that 66% of the array slots are not empty. Okay, so hash values depend on table size, so hashes of entries are changed when resizing, and algorithm can't just copy data from old storage to new one, because we have to rehash the items. So that's why this dynamic resizing is a very complex procedure. We are not able to copy the old entries into the new array, because we have to rehash the items again. And of course resizing takes order n time complexity to complete, where n is the number of entries in the table. And this fact may make dynamic sized hash tables inappropriate for real-time applications. So okay, we have to consider these facts. If we would like to make dynamic resizing, it's okay, but we have to take this order n linear time complexity into consideration, that whenever we resize the underlying array data structure, then we have to rehash the values, and that's why it's going to be a slow procedure. Okay, so what about the applications for associative arrays? For example, in databases, sometimes search trees and sometimes hashing is better. By the way, I'm a huge fan of balanced binary search trees, but okay, we can come to the conclusion that hash tables or dictionaries can be very useful. Or for example, counting given word occurrence in a particular document, or storing data and constructing lookup tables, for example, for password checks. Hash tables can be very useful. Or lookup tables in huge networks. For example, we would like to look up for IP addresses. Okay, it can be done with the help of hash tables. And one of my favorite application as far as hashing is concerned is the substring search. The Rabin-Karp algorithm relies heavily on hashing, and basically these are the applications as far as hashing is concerned, and basically hash tables can have several applications. Thanks for watching.